Okay, let me just open this. All right, so let's get started with our very last lecture. Today we're going to go over a quick review. I'm going just to go over the topics we covered. And I haven't prepared anything, to be honest with you. How I want this to go is that you ask me questions and then we'll go fix these gaps that you may have with some concepts. And if there are no questions, then I'll probably finish the lecture early today. But the idea is really to interact, just to go over this together. And along the way, if you have questions, just ask me, and we'll see if I can help with those. And then at the end, we'll also talk about the final examination briefly. It's on the 19th, so there's still quite a bit of time to get ready. And at the end of this lecture, you notice that here there are 55 slides. I think there are about 20 to 25 slides of review, and then the rest is just practice examples that you can use to practice. And I may get one example from this lecture and put that in the file. And just don't tell anybody. Okay, so let's get started. The first topic, and probably one of the most elementary topics that we started our analysis, was the first order transfer functions. And for a transfer function that only has one pole, the only thing we need to characterize the system is its time response, is its time constant, that will give the time response. Because this has only real poles, we know that the inverse of this will result in exponential responses only. The system is always overdamped. The poles are always real numbers. And the way the time constant influences the time response is that the greater the time constant, the slower the system is to reach a steady state. Once you take the inverse Laplace of this, we notice that the time constant shows up there. All right, so the time constant makes that exponential decay faster or slower. And we can also see here that in this case, the pole is located at negative tau. So depending on the value of tau, this pole may be located on the right side or on the left side of the S-plane. And as we know, if it's located on the left side of the S-plane, the exponential decays to 0 and eventually will bring the system to a steady state. If the pole, however, is on the right side of the S-plane, then the system is said to be unstable because these exponentials will always tend to infinity. Right? So say we have a system with 20 poles and one pole is located on the right side of the S-plane, the entire system is unstable. Right? So the location of the pole influences, first of all, the stability of the system, if it converges or if it goes diverges to infinity. That is only related to the real part of the poles. Right? And for all first order transfer functions, the pole will be real, will be placed on the real axis. Now, two options: it's going to be stable or unstable depending on where it is, and the time response will also be influenced by it. Typically, the farther the pole is from the imaginary axis, the faster it will reach steady state, because the faster the exponential will decay. The closer it is to the imaginary axis, the slower the pole is, the slower the system reaches a steady state, because now this value of sigma here is smaller, which means that it takes more time for the exponential to die off to 0. So that's the easy part. And then we introduce the second order transfer functions. And these are for systems. Most of the system will be second order or higher when we deal with biomedical systems. And to characterize this system, we need a bit more information. We need to know the characteristic equation in the standard format that we have here. And the reason we use this standard format is that we only need to evaluate these two parameters in order to understand exactly how the system will behave in time domain. We don't even need to take the inverse Laplace transform of this to know what is going on. We can simply look at these values, and based on them, we know what the result will be. We have the damping ratio and the undamped natural frequency. So the undamped natural frequency is the frequency of oscillations when there is no damping. The frequency at which when the poles would be placed on the imaginary axis. And the most important thing is the damping ratio, which typically relates in a physical system to the amount of energy dissipation in the system. We can characterize then the time response of the system based on the damping ratio exclusively. If the damping ratio is greater than 1, and this must be extremely clear, the system is overdamped. The reason is that if the damping ratio here is greater than 1, the roots of the denominator, or the poles, will be a real number. You can see here that a greater than 1 minus 1, greater than 1 squared minus 1 is a number that is greater than 1. The whole thing is a real number. So when zeta is greater than 1, the system is overdamped, and we will see two distinct poles that will be placed on the real axis, and these poles will be distinct, and they'll be on the left side of the S-plane. If zeta is exactly 1, well, we can see here that this goes to 0, this goes to 0, and the two poles are exactly the same. They are still on the stable zone, still on the left side, but they are exactly the same. And this characterizes a critically damped system. If we now keep decreasing zeta, and zeta is smaller than 1, then you can see that the result of this operation is now a negative number, which means that the square root of that negative number is a complex number, and you have a pair of complex poles. Now, when you have a complex pole, we'll add an exponential component to the system due to the imaginary part of those poles, and now we start to see oscillations. And that characterizes what we call a underdamped system, when zeta is between 0 and 1. When zeta is 0, there's no damping, there is nothing dissipating energy into the system. So this goes to 0, this goes to 0, 0 and 0. We'll see here that we have negative omega n j and omega n j. So only exponential components will appear in the output, because this doesn't have any exponential component. Because there is no exponential component, the system oscillates indefinitely. There is nothing bringing these sinusoidal components to 0. And that's what we call a undamped system. Now, past the point where zeta is now negative, that characterizes an unstable system, because if we go back here, this exponential for a negative zeta increases indefinitely to infinity, and will bring all other poles also to infinity. The entire system output will go to infinity, regardless of how many stable poles there are. The unstable pole will take over and make the entire system unstable. So this must be extremely clear. This is something really important we need to know. We need to know the influence of the pole locations, what they do to the output without computing the the inverse Laplace transform. And this is also essential in order to understand the idea of root locus. By looking at where the pole is on the imaginary, on the S-plane, we should be able to get a pretty good picture of what is going to happen in the time domain. Right, this is the summary of that. Cases for zeta greater than 1. Cases for zeta smaller than 1 but greater than 0. Zeta equals to 0. And then all the other cases here that tend to infinity, zeta is smaller than 0. Right, so by placing the pole there, we know exactly what is happening in the time domain. Any questions so far?
Sorry, Professor, the one you mark as zeta greater than 0, is that when the zeta equal to 0?
This one right here is zeta equals to 0.
Oh, sorry, zeta bigger than 1, and that point is zeta equal to 1.
Yeah, so let's do it again. So this guy here has zeta greater than 1. This one here has zeta between 0 and 1. This one here, zeta is 0. This guy here, zeta is less than 0 but greater than -1. And that guy there, zeta is smaller than -1.
Where's the point that zeta equals to 1?
In this case, we don't have it here because we would need two poles.
Oh, okay.
Right, two poles located at the same point, then zeta would be equal to 1.
Okay, I got it.
All right, so these 2 points, when the two poles are together at the same point, we see a critically damped system, and you'll see that in the root locus. We'll see that the poles are coming together or coming together to the same point. When they become the same, that characterizes a critically damped system. Past that point, then the system becomes critically damped. And you can clearly see that on the root locus. So that is a very important point to find. 2 points of interest, in fact, when you have a root locus. The first one is the critically damped point, because that's the transition between underdamped and overdamped. And the point where we cross the imaginary axis, because that is the transition to the unstable zone or stable. Any other questions here? No? All right. So we can take this approach even further and place the poles here on the imaginary on the S-plane and identify the real and imaginary components. The real component here is sigma, which is zeta times omega, and the imaginary component is there. It depends on the damping ratio. By placing these two, so the real and imaginary part, I can create this vector. And if you find the magnitude of this vector, we'll see that this is exactly omega n. By simply doing the real part square plus the imaginary part square root of that. And why is that important? Well, because we know that now if we have a line like this, and this pole moves along this line, the farther it is from the imaginary, the center of the S-plane, the faster the oscillations will be. Right? The faster the natural frequency of the undamped oscillations. By doing the similar analysis, we can also relate the angle of this line to the damping ratio. And this angle here we saw is the inverse sine of zeta. We'll be using simple trigonometry. You can try that on your own. It's given in one of the past lectures. So the farther that a line is to the imaginary axis, the greater that angle, the better, in the sense of the more overdamped the system is, the less oscillations we'll see. So anything along this line, for example, any poles along this line would have a constant damping ratio. Any poles along this semicircle here would have a constant natural frequency. So not only we now know what is happening to the time response of the system, but we can also quantify the time response of the system by simply looking at where the poles are. We don't even need to look at the time response in the time domain anymore. We can look at where the poles are, and that tells us everything. By placing a pole here, we already know that this is going to be a underdamped system. By measuring its distance to the origin, we can find the natural frequency of oscillations. By calculating the damping ratio, by this angle, we can find the damping ratio. And once we have both, we can calculate everything. We can calculate the percent overshoot, which is directly related to zeta, and we can calculate the settling time, which is 4 over the multiplication of them. So this is to say that the time response is given here. We can just look at where the poles are, and that's enough. We don't need to compute the inverse Laplace transform. We know exactly where what these poles are doing. As designers, if you want to design a controller, then our job is to take a closed loop transfer function and then put these poles where we want to meet a certain design requirements. By placing a pole there, we are specifying its damping ratio, we are specifying its natural frequency, and specifying the time response. So as we can control where the poles go with the controller, we have all the ability needed to specify exactly what kind of time response we want. Any questions? Nope. Okay. So once we have these metrics, we can now analyze the time response if we wish based on certain metrics. And these metrics that we introduced here are, first of all, the steady state error. We want the system to reach a steady state to a point that is as close as possible to the one we specify. We can also specify how fast it first crosses the desired value. That's the rise time. The peak time, where the maximum value occur. These two are not very commonly used, but most of the time we are interested in the settling time, which is the time it takes for the system to reach or to stay within 2% of its final value. We can see that if I have a final value here of 1, then 2% of it would be a range comprised between 1.02 and 0.98. That's 2%, plus minus 2% of the final value. So once we follow this curve and we pass the point after which the system does not get out of that range, that's what characterizes the settling time. Some textbooks will use 5%, some will use 2%. We're going to use 2%. Right, so that's one metric that tells us how fast the system will settle. And the other one, of course, is the percent overshoot, is how much the system will, of course, exceed the final value. What is the percent overshoot in the overdamped system?
0.
0. An overdamped system is an exponential. It never exceeds the final value. The percent overshoot is 0. Very good. Okay. So why do you need to pay attention to this? Well, because here we have a trade-off between speed and oscillations. In certain applications, we want the system to react fast, and we may afford to have some oscillations before it settles. In other systems, maybe we can't afford to have any overshoot. Let's assume, for example, we have a robotic arm that operates on the eye, and you want the tip of the robot to just touch the eye. So you can control the system, do some sort of position control to make it move, let's say, by 1, as we have here, 1 millimeter, centimeter, whatever. And we know because that will reach the surface of the eye. If there is overshoot, well, the robot will first go beyond that 1 millimeter and then come back. And that will damage the eye in this example. So in this particular case, it is preferable to go slowly and reach the final position than going faster and oscillating around. In other examples, as I said, then because if you want the system to react fast, we may allow for some oscillations. So all depends on the application itself. Here are the metrics we have to analyze all of these by inserting, but all we need here is the natural frequency and the damping rate. That was supposed to be the damping ratio, zeta. And based on these two values, they can calculate everything. So once again, by placing a pole on the imaginary real axis, we have omega n, we have a zeta, and with that, we can calculate pretty much everything we need to analyze the system in the time domain without actually calculating the inverse Laplace transform.
Sorry, did you mean it has to be zeta or zeta to the power of 2?
Zeta squared, sorry, it's just the symbol that
oh, okay, thanks.
that changed. Yeah, that is correct. So if I ask you, for example, a common mistake that I see here is if I ask, for example, calculate the a value of a certain parameter in the system such that the percent overshoot is 0. And then what the students do is that they take this equation here and they equate that to 0. Let's say zeta is a function of a parameter k. So this would be a function of k. This would be a function of k, which is, say, a control gain. And my question is, find the value of k that results in no overshoot. And then the students go here, set this to 0, and try to solve for k. And why does this not work? What is the problem with that approach? Why you cannot equate this to 0?
e to the power of that never goes to 0.
That's true. That's true, but it's more fundamentally, this equation only works for a underdamped system. It was derived by taking this equation here, taking the derivative of the equation, finding the peak time, replacing the peak time in the resulting equation, and then to find the maximum overshoot. So this can only work if the system is underdamped. For overdamped systems, this doesn't work. So this can, because it's only underdamped, zeta needs to be between 0 and 1. It doesn't work for zeta greater than 1. It doesn't work for zeta smaller than 0. And if you're dealing with a underdamped system, then this can never be 0, right? Because if the overshoot is indeed 0, then zeta needs to be greater than 1, and this is outside of the bounds we have specified for this function. Okay. Next topic was block diagrams. It was the last one we saw, both creating a block diagram and simplifying a block diagram. So at this point, I believe you are able to appreciate how useful it is to create a block diagram, because you can import data directly into a software such as MATLAB and do the entire analysis of the system there, as opposed to having a single transfer function that gives the relation between the input and the output. Here we have several transfer functions in cascade, which means that we can probe the signal at any point in this graph. The signal there could be something of interest, for example, speed, velocity, speed, position, acceleration, voltage, current, charge, and so on. So having a combination of block diagrams allows us to go and probe the signals there. If you only had the transfer function y over r, or the other way, sorry, r over y, then this becomes a transfer function and you only have the information between the input and the output. You cannot access any internal variables. So you have here three, yes.
Sorry, shouldn't it be y over r?
Yes, sorry, yeah, I was right in the first place. Output divided by the input, yeah. Yeah, thank you. Okay, so we have three fundamental operations that we need to master. The first one is to obtain a block diagram from a transfer function. Convert a transfer function into a block diagram. Then the second one is to obtain the transfer function from the block diagram and to simplify the resulting system. So you need to be able to, given the equations, create the block diagram, given the block diagram, create the equations, and given the block diagram, create the entire transfer function between the input and the output. There are several examples in the last lecture, and you are very likely to find one in the final examination. Simplify a block diagram. Given this block diagram, what is the final transfer function? Y over r. Right. So this is likely going to be one question in the final. Any questions here? Anything that you need clarification on? No?
Can we just can we just write the general form of a closed loop block diagram transfer function for when the feedback is negative and when it's positive? I mean, when there's a negative sign and when there's a positive sign.
You mean something like this? Let's call this C, like that, and then change this.
Yeah, exactly. Yeah.
So let's call this R and Y. So for this one, what do you have? What is the expression for Y? Y is this point here, which is
R
this
minus,
signal times C. So R minus
Y times D.
Y times D.
The whole thing times C. Yeah.
everything times c. So is this, does anybody have questions here? Does this equation make sense? Yeah, okay. So now we can multiply this out and move all the y's on this side here. It's going to be y. So 1 plus, when you move this thing to this side, c times d. Right, y dc. Moving y to this side, you have y plus y dc, factoring out y, equals to rc. Now we can find y over r as c over 1 plus cd. If this is a unit feedback loop, then this is then d is 1, and you just have 1 plus c. Now, if we place, you have the same system, but now you have a positive value. What do we have? What is the expression for y now?
C over 1 minus CD.
Yes, but what is the expression over here? Let's go from the beginning. R minus
plus yd
plus dy times c. All right, now notice that when I multiply this out and move this to this side, now it becomes negative. We have y1 minus dc or cd equals to rc. So now y over r is c over 1 minus cd. All right, so this positive sign came from this negative sign. This negative sign came from that positive sign. And again, if this feedback loop here turns out, if it doesn't have a block, it's just 1, then d and d here would be 1. Okay? Are we good here?
Yes, thank you.
Yeah. Anybody else has questions? No? Okay. So once we find the transfer function and we look at the time response, or you look at the characteristics of the time response based on where the poles are, the main thing is to ensure that the system is stable. An unstable system has no practical use. If you develop a controller, we want that controller to be stable. So you can look at two things. You can look at an open loop and closed loop stability. If you have a system such as this one, we have a controller and you have a process like that. This is an open loop system. For this system to be stable, we need the poles of the transfer function c times g to be located in the stable zone, to be located on the left side of the S-plane. If we now close the loop, and we want the system to be stable, what is the condition? Well, the condition now is that the poles of the closed loop transfer function must be placed in this stable zone, and the closed loop transfer function will look like c times g divided by 1 plus c times g. So for the open loop, we dealt with the characteristic equation of this function c times g. For the closed loop, we now need to look at the poles of this equation, 1 plus c times g, because this is the characteristic equation of the closed loop system. The system might be open loop is unstable and closed loop is stable, or the other way around. Right? But notice that what we are doing is that we take the system, we find its final transfer function, regardless of it is an open or closed loop, and always look at the location of the poles. If the poles are on the left side of the S-plane, then the system is set to be stable. Now, one way to find where these poles are is, of course, to just look at, using software, the roots of the polynomial and see where, if they all have negative real parts. If they all have negative real parts, we are on the left side of the S-plane. Everything is stable. Everybody's happy. but that entails that we must have all the coefficients in the polynomial. If a coefficient in that polynomial is unknown, such as, for example, a control gain that we want to tune, or a parameter in the system that is changing over time, that it cannot be given a specific value at a given time, it's a bit complicated. And then that's where the Routh-Hurwitz stability criterion comes in. The idea is to look at the characteristic equation of either the open loop if you're evaluating open loop stability, or closed loop if you're evaluating closed loop stability. So for example, here, if I'm giving you this system with C and G functions that are specified, and I ask you to evaluate stability, you first need to find a closed loop transfer function before proceeding to the use of the Routh-Hurwitz criterion. The idea of this technique here is relatively simple. We will just have to populate this matrix. We know how to do that, and then we look at the number of roots with positive real parts. Excuse me, the number of roots. We look at how many times the sign changes in the first column, and this will indicate the number of roots with real positive or negative parts. So if everything in the first column is positive or everything is negative, that indicates no sign change, which means that all poles are on the left side of the S-plane, the system is stable. If we see a sign change happening here, that indicates that at least one of these poles are located on the unstable zone and the entire system is unstable. For example, if this point here changes sign, we will have two sign changes from this point to that point, and this will characterize two unstable poles. If we have the last one here is changing sign, we only have one sign change, and this will characterize the fact that I have one unstable pole, one pole on the right side of the S-plane. And this analysis must be consistent with the root locus. If you plot the root locus for a given transfer function and you look at the Routh-Hurwitz, we should see the exact same behavior. We should be able to compare them. That, for example, the system is always unstable. Let's say if this point here was negative, and we should look at, if you look at the root locus, we might see something, I don't know, something like this, for example. And this is perfectly consistent with the Routh-Hurwitz, because the Routh-Hurwitz says that, oh, there is two unstable poles, and here we see also two unstable poles regardless of the value of a constant of the gain k. Right? If we see, for example, the last one changing only, this one is changing, and let's say this is a value, this depends on a value of a parameter k, and it is positive or negative depending on the value of k. If we look at the root locus, we should see something that tells the same story. For example, I don't know, for example, something like this, where this pole is initially unstable, past a certain value, it becomes stable. So when you look at the Routh-Hurwitz, we should see that for a certain range of k, let's say k between 0 and k1, this value here is negative, the system has one unstable pole, and then from k greater than k1, the system has 0 unstable poles, this becomes positive, and the entire column becomes positive. Where is k1 on the root locus? Well, k1, the value of k1 that makes the system enter the stable zone is right at the origin in this particular case. Right? So when you analyze both the Routh-Hurwitz and the root locus, they must tell the same story. All the values you get from one must be consistent with the other. If the Routh-Hurwitz shows you that for a certain range there are two unstable poles, the root locus must show exactly the same thing for the exact same range of that parameter of interest. Okay? So this link between the root locus and the Routh-Hurwitz must be very clear. And you probably notice that I'm insisting on that point on the last assignment, right? Because it is indeed very important to make this connection. Any questions here? No? Okay, so we know how to populate the Routh-Hurwitz. I think I'm gonna skip that, right? Or does anybody want me to go over this? How to populate the Routh-Hurwitz array? No? Yeah? Okay. There are no questions, then I'm gonna move on. And here we are with the root locus. So for the root locus, what is the root locus? Well, the root locus is simply a map of all possible locations of poles in the system. When you look at the root locus, and you will see something like this, for example. We see here 2 poles and 2 zeros. What are we actually looking at? Any point on this graph represents poles. We are not looking at zeros. We are looking at poles. Any point on this graph is a possible location of a pole for a given parameter of interest. It turns out that the way the poles travel, as we control again in the following, for example, but following this characteristic equation here, 1 plus k times L equals to 0. L is a function of S. It may have poles and zeros. In this case, it has 2 poles and 2 zeros. And k is a parameter that we are changing from 0 to infinity. For any value of k, we are placed in one point along this root locus. And this represents a pole. It does not represent any zeros. The zeros are here only to indicate where these poles will end up. It turns out they go towards the zeros in this particular case. But we are never looking at a zero here. We are always looking at a location of pole. Any point along this curve is a pole, is where the pole ends up given a certain value of k. K equals to k1 would be here, for example, which means that when k is k1, that's where the poles are, right? And if you keep increasing the poles in this particular case, they are going to go towards the zeros. But these zeros do not represent zeros of the closed loop transfer function. They simply indicate where the poles are going to. Now that distinction needs to be very clear. Let's take a look here at one example. We want to analyze the influence of this parameter A in the closed loop transfer function. In the time response, on of course, in the closed loop transfer function. So the first step is to write the equation, the characteristic equation in this required form, 1 plus A times a function of S, and equate that to 0. In this particular case, when you do that, you see that the characteristic equation will be not in the format we want. So you need to prepare the equation in that format first. And here is one example that is directly related to the assignment. We can manipulate this equation, and after a few steps, we just multiply this out. Group elements that have A and don't have A, and then simply divide everything by the group of elements that doesn't have A, and this will create the function the way we want. Once this is done, now we can use MATLAB with the function rLocus to create this plot. And what exactly are we looking here? Well, from this particular example, we are varying A from 0 to infinity when A is 0. The poles are placed here. And as A is increased, we see that the poles are coming together at this point. One is moving towards the 0, one goes to negative infinity. Now, based on this root locus, what is the influence of A in the time response? Let's call here that at this particular point, A equals to A1. What can you say? For which range of A is the system underdamped?
Greater than A1?
For which range of K of A is the system underdamped? Underdamped.
A to A1.
A to A1. So between A and A1, between 0 and A1, we are along this line here. And the system is underdamped. When A equals to A1, we see the two poles at the same location. That characterizes a critically damped system. And for A greater than A1, what happens?
Overdamped.
Overdamped.
Overdamped, exactly. A greater than A1, overdamped. So again, this is a particular point of interest. This is the critically damped point, where the system goes from underdamped to overdamped in this case. And we can calculate that point by calculating the breakaway point. To calculate the breakaway point, we would set, in this case, A to P of S. So solve for P of S, take its derivative, equate that to 0, and that gives us that point. It doesn't give the value of K at that point. It gives us the point where these poles are meeting, right, by simply doing the derivative here. And once that point is known, then you can evaluate the function at that specific point to find the value, the precise value of A there, right? So there's a bit of a confusion I see sometimes between the root locus and the route Hurwitz. The root locus will give us this map of what is going on, and will give us the value of K there at the breakaway point, if there is any breakaway points. The root locus will give us this value here. It doesn't tell us anything about overdamped, underdamped, or whatever. It only tells us if the system is stable or unstable, and if it is unstable, how many unstable poles we have. The root locus will give us the entire picture of the system, but it won't give us this particular number here. It will give us that one through the breakaway point. So a combination of the two is required to evaluate the entire system. Another confusion that I see here is when it comes to the root locus breakaway point. Let me just draw an example here. Is when you have more than one breakaway point. And I can see that confusion. You have all the right to be confused about that because I did not explain it. Just give me 1 second. Hopefully this is the last semester writing on this board. Next semester is in person, at least for me. Okay, so let's assume that we got a root locus that resembles something like this. So this pole goes to negative infinity. These two guys come together and then they go like this. Let's assume that this value here is -1, -2, and -3. Actually, let me put another pole here and make these guys go like that. Yeah, and -4. There you go, like that, which is fine. Yeah. And let's assume we calculated the breakaway points, and we found if you do this, we have a 4th order polynomial. So when you take the derivative, that's a 3rd order polynomial, which should result in 3 breakaway points. Let's assume that one of the breakaway points was -0.5, one was -1.5, and one was -3.5. What do we do with these points now? There's only 2 breakaway points, and we found the 3. Well, first of all, the breakaway point must be part of the root locus. If it's not part of the root locus, it's not a breakaway point. So this one is -1.5, and you can see that it lies on a range here where there is a root locus. So this is a breakaway point. This one is the same. There is between -3 and -4, and there is some root locus there. So this is also a breakaway point. And this one is -0.5, is on a portion of the S-plane where there is no root locus. So that is not a breakaway point, and that one can be neglected.
Excuse me, Professor.
Mm-hmm.
So for this case, if we have like several roots, several S, so we need to analyze it according to the graph, Right. Otherwise, okay. Okay. Good to know.
You cannot tell. Yeah. Otherwise, you cannot tell. One thing that you would be able to tell right away without looking at the graph is that if you end up with a complex number, let's say you have a system with a fourth order polynomial and two of these roots are complex. Right? Two of the breakaway points are complex. This is not a breakaway point. Why not? Because the breakaway point must lie on the real axis. Right? So if you end up with complex values as your breakaway point, you can run into that for sure, but you can always right away disregard that value because it's not on the real axis. And if it is on the real axis, then it must be within portions of the real axis where there is a root locus. Okay. Now, another confusion that I see here very often is that these points are the breakaway points. This is this point here and is that point there. These are not the values of k. If you want to evaluate k at this particular point, then you need to go back here to our transfer function. So let's say we use this characteristic equation. We can set p of s to k, which means in this case makes p of s equals to -1 over h of s. Then you take the derivative of this, equate that to 0, we found these points. Now, if you want to see what the value of k is here and here, then you need to evaluate p. Let's call this S1, S2, S3. P of S2 will give us the value of k here. P of S3 will give us the value of k there. P of -0.5 doesn't mean anything because this is not a breakaway point.
Okay. Sorry, can I ask you? Oh, sorry, can I ask a question? Thanks. So in the assignment for the first question, we have kind of the same root locus graph, and then we end up with 3 values for S when we want to calculate the breakaway points. And they all seem to be a possible answer. How can we cross out one?
No, they can't. They can't. There's only 2 breakaway points. The third one must be outside of those bounds. If you found 3 points with only 2 breakaway points and 3 values that fall within these ranges, then there is a mistake in the calculation.
Oh, okay, thanks.
Can I just ask a question about how we use the root locus method as a whole and how we find the characteristic equation?
Yep.
Okay, so I know that when we have that 1 plus ka equals 0, we're just taking that from our transfer function like y over r. Do we care about what's in the numerator at all, or is it just about the denominator? Because I know this is about the poles and not the zeros, right?
Yes.
Okay.
Let's see. Well, let me give you an example here.
Sure.
Professor?
I would say yes and no. Yeah. Let me just do this example, then I'll take the next question. Okay. Let's assume we have a system like this. So this is S plus, well, actually pretty much what he had there. Let's do S plus A, like that. All right, this is a negative sum. So the characteristic equation here is the entire transfer function would be S plus A divided by 1 plus S plus A. All right, we can factor out the whole thing here, and this is going to be S over, what do you have here? S plus A plus S, which is 2S plus A over S plus A. So this one cancels that one, 2S plus A. Right, this is the entire characteristic equation. We are dealing with this, but you see here, because this is the characteristic equation of the closed loop transfer function, which is the same as this. And they are the same. This equals to 0 and that equals to 0 is the same. We already, the 0 of the open loop transfer function made it here. It's influencing both the numerator and the denominator. See this S here came from the top. Like came
Yeah,
from
that makes sense.
that, right? But now when we are using this equation, we are doing 1 plus s plus a to evaluate now the location of the poles. We don't need to worry about the zero, because the zero is only affecting transients. It's not affecting the steady state. It's not affecting the shape. It is affecting the steady state. It's not affecting the it doesn't dictate the shape of the output. It will influence the shape of the output, but not exactly how the system behaves. What we need to look at is the poles, and the poles are given by this characteristic equation that already have been influenced by the effect of the zero, because you have 2s here.
Okay, that makes sense. Thank you.
Yeah. Had another question.
Yeah, my question is related to the one you talked before. Can you just redraw that picture?
Yeah.
Sorry. So I just want to ask, well, this one is more related to the assignment, because for the assignment, actually I got 3 roots and I eliminate one of the root because it doesn't make any sense on the graph. And then I analyzed the other 2 roots, but the case is that that 2 roots make me, well, I got the same K for that. So I just want to ask, is that true? If we have this kind of graph, we will always got the same K, or there can be different K for this kind of situation?
They will be the same. Most of the time it'll be the same. The
Okay.
K here, I think you got K equals to 10 or 1?
1.
1, and K equals to 1 here too, right?
Yeah, exactly.
Which is good news, because now you know that when the system reaches, when K is equals to 1, both these 2 sets are here, these 2 poles are there, the system is critically damped for both sets of poles. And then past 1, everything becomes overdamped, right? But if we add something different, let's say K, I don't know if that could happen. In practice, I can't think about a function that would give that, but let's say you would have K equals to 10 here and K equals to 1 here, which is very unlikely to happen in practice, but let's assume that. Then your system would become critically underdamped for K greater than 1.
Yeah.
Right? And then you would just have more oscillations coming after K equals to 10, but this one would trigger the underdamped zone.
Oh, okay. And that means there is 2 critical damped point.
There would be 2 critically damped points, yes. But once you pass the first, you already have exponential. Doesn't matter where the second is, the system is already underdamped.
Oh, yeah, you're right. Okay, I got it. Thank you.
Any other questions here? No? Okay, last topic, PID controllers. Very important topic. We use 3 lectures to go over this, and this table that I'm showing here is very important. You don't need to memorize this table, because if you memorize this table, you don't learn anything. What I wanted to do is to understand why we have these conclusions here. Why increasing the derivative gain decreases overshoot? What is the principle behind that statement? Not necessarily the statement itself. That's all, everybody can memorize that. But why exactly increasing KD decreases the overshoot? These fundamental understanding of how each element in the PID controller affects the time response is fundamental. For example, how why increasing or having an integral gain eliminates a steady state error. Why is that? Right? Beyond just looking at the table and saying, oh, Ki leads to 0 steady state error. The effect of the integration and the effect of accumulating an error, and so long as there is an error, we'll keep increasing the control action to eliminate it because of the integrator. That needs to be extremely clear. Right? So all these 3 elements have their function, what they do, and most importantly, how they do it must be very clear. Are there any questions about a PID? No?
Yeah, just a quick question. I remember you were going over this in one of the previous lectures, but you mentioned that when we're tuning a PID controller, we can kind of break it down and use like superposition to analyze each like a gain. Is that a real thing, or am I just imagining that's something that we did?
No, we didn't explicitly use superposition. We did a proportional, then a derivative, and then a proportional derivative integral controller, one at a time. But we didn't do superposition. But we could, yeah, we could. But I don't know if that would. I doubt that it would help with tuning. I think I need to do all three at the same time.
Sounds good. Thank you.
Any other questions here, folks? No? Okay. Next was the Ziegler-Nichols PID tuning. This one, it's more for your information. If you ever have to tune a PID controller, you can come to these charts here. Two different methods that we saw. The first one, we need to bring the system to instability to find the ultimate gain, ultimate period, then populate this chart. The next one, we can simply look at its time response, infer some parameters from the time response, and based on that, we can find appropriate gains for Ki, Kp, and Kd. I'm not going to be asking anything about this on the final examination. This is more for your information. If you ever have to develop a PID controller, this will be useful. And if you're doing any sort of control system applied to biomedical engineering in your fourth year project, it will likely end up doing something like this. So here is just for your information. I'm going to skip that. And the very last topic we discussed was Bode plots. I think from experience, it seems to be one of the most challenging concepts for students to grasp. But what we want with a Bode plot, and I'm going to do this one a bit fast, is just to represent the phase and magnitude of a transfer function. And why do we care about that? Because that gives a sense of how much a signal will be amplified or attenuated once passed through a transfer function. So for any system, any electrical component, for example, or electrical motor, anything like that, where there is an output and there is an input, there is an output, that it can happen at the various frequencies, we want to know how much that input will affect the output. And depending on the frequency of the input, will have more or less effect on the output. And for most electronic systems, when you buy one, electronic components, you will see a Bode plot. And what is the Bode plot? It's simply a representation of the phase and the gain of a transfer function. And that gives us all the information we need to understand how the system will respond to a changing input frequency. And it has many practical applications. This is probably, I would say, modeling is very important. We'll see that everywhere. Bode plot is one of those also examples that I will encounter at any time you as engineers, as you are required to develop something, to design something, you will certainly be looking at a Bode plot of components you buy. How we built a Bode plot? Find the elements, the individual elements that will affect the Bode plot. Constant gain, pole at the origin, zero at the origin, real poles, real zeros, and imaginary poles and zeros. We find their slopes. We find their influence on the time response, on the phase, excuse me. And by looking at these individual building blocks, we simply add them up together, and this gives us the representation of the entire system. This gives us, as I said, a pretty good idea of how a system behaves, at which range of frequencies we are looking at. So probably one of the most important topics we covered when it comes to practical applications. And of course, the controls part and the modeling as well. The very last topic I'm going to review quickly, just one slide here, is the state space representation. This goes back to simulation. The state space representation is just another way of representing equations. And why do we care about this? Because in this particular example, we can have our variables of interest highlighted in a simulation. If you want to, let's say, analyze an electrical circuit, there are certain elements in that circuit that we want to pay particular attention to. We can design the system to highlight those variables in the simulation, and we can explicitly have access to them when we simulate the behavior of that system. We typically choose these variables to be elements in the system that can store energy. And the idea is relatively simple. It's just, again, another way of representing the equations. This time we represent them in a matrix form. Another advantage of this is that we lower the degree of the transfer function of these equations. If you have a system of, let's say, a fourth order system, we'll be representing that fourth order system with 4 first order differential equations. We lower the degree of them. And they will, of course, be interconnected, but in the process of doing them, then all these equations will be kind of highlighted. All these variables will be highlighted in the simulation, readily available for to be examined if you have to. So this is also a very important topic. There are entire classes that are only based on a state space model. If you want to take one as elective, let me know. And it would be the exact, would only be based on the state space model. There is a whole theory, a whole field there that deals with space state model rather than Laplace. So we are basically replacing Laplace with linear algebra and doing the entire analysis that way. Okay. So these are the main topics that I wanted to review today. Here, this is slide 21 up to slide 25. There are several review exercises that you can attempt. And you see the final answer here. I won't be posting the solutions. You have the final answer at the bottom. You have solutions for how many exercises we have? 23 lectures, about 5 exercises per lecture. So you had like over 100 examples with full solutions. These ones, I won't give you solutions. The final answer is there though. Attempt them, and I might pick one here to put in the final. Okay, so that's all of it. Now let's take a moment to just think of what we did in this course. We went from a very basic modeling of different system, electrical and mechanical system, very simple equations. And we are able to simulate them in many different ways using the transfer functions, using the state space model. You're able to analyze them in the frequency domain, able to analyze how we can change the behavior of that system using an appropriate control, and even dealt with some sophisticated ways to control it, to how to move the poles around, how to make sure that the system follows the behavior we want. So that's a lot of content packed here. It went a long way from the very simple modeling again to Laplace transforms to model them, then create these transfer functions, analyze these transfer functions in time and frequency domain, and control it. There's a lot of theory here, a lot of stuff, and it's for sure a very useful. These are all very useful content to know. Some of them may seem a bit abstract at a time, but I can guarantee you that not a single slide in this course is there just because I'm supposed to teach some theory. They are there because they are useful, and you will encounter some of this theory in your next courses. And all of what we saw in this lecture has a very strong applications in biomedical systems, from modeling to control and simulation. It's something that as a designer, you will be dealing with for sure. So that's it, folks. That concludes our course. That's the last one. That's the last lecture. I really hope you enjoyed this course. I know that we are doing this online, so it's not the same as in person. I hope that this setup here was a bit better than just looking at a screen and a PowerPoint at home. And hopefully this is the last semester. Next semester, things will start to go back to normal. I'll be on campus. If you are around, stop by my office, say hello. I can put a face on these voices that I've been hearing from for the last 4 months. You have seen me, I haven't seen you. So if you are around campus, just stop by. I'm in Canal Building. Stop by, say hello there. And if you're interested in research opportunities, some of you have already contacted me. Take a look at my lab website here. See what we do there. Come talk to me if you have your own project that you want to pursue and it's not listed in my current lab activities. We can always talk. If you have and it's something you want to develop, come see me. We can talk about it. Research, development, undergraduate opportunities if you want to do part-time or full-time research. If you want to do a 4th-year project based on one of the research topics that I have, contact me early in the summer, and we can discuss opportunities there. And of course, if we are doing your 4th-year project and you have something in mind you want to develop, you want to propose your own project, that's perfectly fine. Just form a group, come up with your idea, and we can see if that makes a good 4th-year project. If not, we can discuss alternatives, things that I can assist you with. And of course, when you graduate, if you are interested in pursuing graduate school, I always welcome good students. Okay, so all the information is here. Also feel free to come by the lab, see what we do there sometime. It's in Canal Building. If you're around, just stop by and show you what kind of research we do and how this course and other courses can be applied there. And in general, if you need anything, I'll be on campus. Feel free to send me an email, stop by if you need help with anything. I really enjoy this class. I found this semester to be pretty good. A lot of interaction with students, a lot of questions, a lot of people showing a strong interest for the topics we covered. And again, I do hope that you enjoy the contents you saw here. And that concludes our course, folks.
Thank you, Professor, for a good semester.
Thank you.
Thank you.
Thank you. No problem.
Professor.
Your whiteboard has been really fun to look at. Makes it interesting.
Cool.
Makes the lectures much better. The whole whiteboard setup you have. Thank you.
Glad to hear.
Thank you so much. You did an awesome job at teaching us the whole semester.
Thank you.